Hello, my name is Henrique and I am a PhD student at the University of Edinburgh. In this video, I am going to present our recent work on the robustness of legged robots against external disturbances. Let's start by considering a legged robot with manipulation capabilities. In our lab, an example of such a platform is this quadruped robot, which has been equipped with an additional robot arm. When these kinds of robots are deployed to solve real-world tasks, they deal with numerous kinds of uncertainties. And if an unexpected force is applied to the robot, for example the one shown here in yellow, it may cause the robot to deviate from its original plan, possibly leading to failure. One reason for failure could be that when the robot is trying to resist an external force, it tries to use more torque than what its actuators are capable of delivering. Another reason could be that resisting a disturbance would require unrealistic contact forces, or contact forces that would cause slippage given the friction coefficient at the contact points. In unfortunate situations, failure can be due to both these reasons simultaneously. In this work, we present a method to increase the robustness of robot trajectories against unknown disturbances. Some researchers have proposed robustness controllers before. However, we focus on increasing robustness at the planning stage. We believe that considering robustness during planning is important because it can help us avoid motions that are difficult to execute altogether. Another reason is that robust plans can provide any tracking controller, including robust control schemes, with greater margins of control authority. In order to plan whole body dynamic motions, we use trajectory optimization. Our framework implements a method called direct transcription. This method works by converting the original motion planning problem, which is continuous in time, into a version that is discrete in time. For that, we divide the trajectory into a finite set of points, and for each point we describe both the system state and the control inputs. As such, the decision variables of the numerical optimization are the joint positions and velocities at every point, as well as the torques commanded to the robot and the ground reaction forces. In this slide, they are shown as Q, V, tau, and lambda. This representation of the trajectory is redundant, and so we need to enforce the whole body dynamics with this nonlinear equality constraint. We also define additional constraints for the positions of the feet and the end effector. And finally, we constrain the ground reaction contact forces to lie within the boundaries of the linearized friction cone. This formulation is the basis of our optimization framework, and we can use it to plan feasible motions. But we are not only interested in planning feasible solutions. What we really want is to optimize the robustness of the trajectories, and for that, we need the robustness metric to define an objective function. In previous work, we have proposed an exact representation for the set of forces that the robot is able to resist, given a nominal trajectory and its actuation limits. We have also defined the robustness metric based on the magnitude of the smallest unrejectable force, which is given by the radius of the largest ball that can be inscribed in the residual force polytope and centered at the robot link. In this example, it is centered at the end effector. We can take this metric and integrate it in our optimization problem as an objective function, and that's how we maximize the robustness of trajectories. In this diagram, the polytope was defined for a fixed base manipulator, but we can also define it for floating base systems, and include friction cone constraints in addition to the actuation limits. However, when we extend it to floating base systems, computing the robustness metric becomes very computationally expensive, and it can take several hours to compute one instance alone. And this is a big problem because during the optimization of the trajectory, the metric needs to be computed for every point in time. And it does not only do this once. In fact, the solver can take hundreds of iterations before converging to a locally optimal solution. When we add up all these factors, we end up with an optimization problem that would take several days to complete. And this is the problem that we tackle in this paper. With our proposed approach, we can optimize robust trajectories that would previously take days to complete in just under an hour. And that's what I'm going to explain now. Our proposed approach involves considering a virtual force that is applied to the robot. We denoted it here with F. We also consider two instantaneous gain matrices, K tau and K lambda, which map the torques and the contact forces required to resist that force. As we can see from the second equality in this slide, the matrices k tau and k lambda should cancel out the force F. If we do not consider the actuation limits or the friction cone boundaries, we would always be able to find some matrices that are able to cancel any arbitrary force. But in reality this is not true, and the torques that a system can use to resist a force are limited by its actuation limits, as well as the torques that are required at a specific point in time by a nominal trajectory. The same is similar when we consider contact forces. An important note is that we cannot consider any arbitrary matrices that satisfy only the second equality. Rather, they also need to satisfy the two inequalities shown here. A complete derivation of these constraints is given in our paper, but I will try to give some visual intuition of what is happening here. Imagine that these sliders are the torques commanded to the robot at a specific point in time during a trajectory. For a given force direction, the matrix k tau helps us find the maximum force magnitude we can resist in that direction without exceeding any of the torque limits, changing the torques from this to this. Similarly, consider this friction cone and the contact force inside it. The matrix k lambda helps us find how much force we can resist in a specific direction without exceeding the boundaries of friction. After deriving these constraints, it is now possible to go back to our framework and formulate a bi-level optimization problem, which not only finds a feasible trajectory, but also maximizes our robustness metric. Let's have a look at that now. First, we extend the vector of decision variables to include the gain matrices as well as a scalar representing the magnitude of the smallest unrejectable force. Here, we denoted it with ρ. To maximize robustness, we simply need to define an objective function that maximizes the sum of all the rows. Finally, we need to add some extra constraints, the ones from the previous slide. And we also need to limit ρ to be greater or equal than 0, because the magnitude of a force can only be greater or equal than 0. This new version of the problem is mathematically correct, but unfortunately it is quite complex to solve due to the extreme nonlinearity of the constraints on the matrices k tau and k lambda. But there's a way to make the problem simpler, and it is by exploiting the problem structure. You see, in fact this equality right here is made up of stacked Jacobians, and we can reorder the terms and split it into two parts. The top part concerns only the floating base of the robot, and the bottom part concerns the legs and the arm of the robot. By doing this, we can see that k tau can actually be obtained as a function of k lambda and ρ. And therefore, we do not need to have k tau in the decision variables. Also, by obtaining k tau in this way, the bottom part of the equality is satisfied implicitly, so we don't even need it anymore. However, we still need to enforce the top part of this equality, shown here in blue. But now we no longer need the original constraint. So overall, we decreased both the number of decision variables and the complexity of this equality constraint. This is the final version of the optimization problem in our work, and it is now in a form that is tractable for off-the-shelf nonlinear solvers. So let's now have a look at the results. We evaluated our approach for a pick-and-place task in 4 different scenarios shown here. The step scenario, with flat slabs at different heights, the ramp and valley scenarios with steep slopes, and on an extreme handstand scenario. The plots show the results for each of those scenarios. The x-axis is time in seconds, and the y-axis is the smallest unrejectable force in newtons. The blue series show the robustness of the initial seed, which we computed using our framework to solve the optimization feasibility problem. In turn, we use this feasibility trajectory as the initial seed to solve the same optimization problem, but now maximizing our robustness metric, shown in green, and to minimize torques, shown in orange. First, let us analyze these 3 scenarios. We can see that both the objective functions we tested were able to improve the robustness of the initial trajectory. However, we can see that using our metric we can achieve better robustness than the minimization of torques. These observations were true for all these 3 scenarios. Now, let's focus on the final scenario, the handstand. The robustness plot is significantly different from the other scenarios. We can see that our metric was able to improve the robustness of the trajectory, even if ever so slightly. In contrast, we can see that minimizing the torques actually decreased the overall robustness of the trajectory. So why did this happen? The explanation for these results is related to the task itself. For this task, the robot needs to support all of its weight using only 2 legs. The other 2 legs are pressing upwards against the ceiling and are mostly used for balancing purposes. Our metric was able to improve the robustness because it is able to improve the contact forces on all the contacts, even if it means trading off some torque for that. On the other hand, the torque minimization does not reason about contact forces, and for this case in specific, it is not an adequate metric, because minimizing the torques leads to a solution where the robot is exerting less force against the ceiling and the floor, and therefore decreasing the overall robustness against the disturbances. To validate the whole body trajectories computed with our framework, we tested them in full physics simulation. We also validated them through experiments on the real robot. In this video, the robot is on a scenario with flat surfaces at different heights. Then, we replace the slabs with a skateboard. The bearings on the skateboard significantly change the friction coefficient along the rolling direction. To test robustness against contact uncertainty, we purposefully did not update the friction coefficient on the contact model. But the robot is still able to complete the task reliably. This next video shows the robot on the ramp scenario, which is challenging due to the slopes with a grade of 47 degrees. Before I finish, I would like to mention an interesting direction for future work on this topic, which is robustness through environment exploitation. In this work, we have focused on robustness in worst-case scenarios, that is, we tried to maximize the magnitude of the forces the robot is able to resist in every possible direction. However, it would be interesting to exploit prior knowledge of the robot's environment. As an example, consider the sketches on this slide, where a robot is tasked with opening a door. If the robot is operating in a new environment, it may not know how heavy the door is, or how much friction there is in its hinges. Nonetheless, by using techniques from computer vision and object classification, the robot may be able to take an educated guess on how the door should open. For the case on the left, the door rotates over its hinges, while the scenario on the right shows a sliding door. Knowing this can allow us to focus our attention on maximizing the robustness in these specific directions. In our paper, we suggest 2 additional avenues for future research, so please go check it out if you're interested. This is the end of my presentation. I would like to take this opportunity to thank my co-authors, Wolfgang, Vlad, Wouter, and Setu. Without their help, this work would not have been possible. If you have any questions regarding our work, please do not hesitate to contact me at any point in time via email or during the IROS 2020 conference. Thank you very much for your attention.